All right. Hi, everyone.
Welcome back to section 6.2. And in this video, we're going to solve our first second order linear differential equation with functions of x as coefficients, as you see right here. And, no better way to do that with Airy's equation. Okay, so Airy's equation is actually very interesting if you want to research more into it. It's diffraction of light, diffraction of radio waves around the surface of Earth, aerodynamics, deflection of uniform thin vertical column that bends under its own weight. So it's very interesting and very applicable. So what I want us to do is solve this differential equation. So we're, our goal is to get two power series solutions. So our solution is going to be like, some A naught times Y1 plus A1 times Y2, where Y1 and Y2 are our solutions, okay? So that's going to be our goal. So keep that in mind for everything that we're doing. But this is a typical way to solve a power series differential equation method. So let's see, let's get started. So that's our differential equation. So here's our solution, getting started on that. Um, it's already in standard form, or let me rewrite the differential equation. Y double prime plus xy equals 0 is already in standard form. Okay, that means, y double prime is naked. So I don't have to divide by anything here at all. So that means, there's no analytic issues, right? There's no domain issues with any x value. Or we could say it like this, like, you know, p of x equals x, or p of x equals 0, q of x equals x. And so that means there are no domain issues. That means we are, you know, every finite value of x is an ordinary point. Okay, so what does that mean for us? Well, that's great news for us because therefore x equals 0 is an ordinary point. Okay, so the power series, or I'll say so a power series centered at x9 equals 0 will converge. Okay, so that's great news for us. So we're going to consider the power series solution y equals the sum of n equals 0 to infinity a sub n x to the n. You could think about it as, x minus 0 to the n, but we don't really need to write that because it's a bit redundant. So we could just say x to the n. And that works great for us, and it makes life a lot easier for us than having like x minus 1 to the n or something like that. Just takes a lot more effort. So we're just taking it to x to the n. So great. So the previous couple steps you could definitely do in your head. You don't need to write it all down in language like I did. You can just assume that this power series is analytic at 0, and you can just use, you know, this power series solution. And so we're looking at a differential equation, right? We're looking at y double prime plus xy equals 0. So I'm going to need a second derivative because I got to plug in these power series. So, we could check out that, you know, y prime, if we take the derivative of this power series, is something we've seen previously, that it would just be like n times a sub n x to the n minus 1. just using the power rule, and y double prime, which we're actually going to use, excuse me, this would be n equals 1. We take a derivative, the index shifts up. So the second derivative would be n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2. So those are our y and y double prime that we're going to plug into the differential equation. So then plug into the differential equation. Okay, so we're going to plug y and y prime into the differential equation. Okay, so what we will have is the series n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2, plus x times the series n equals 0 to infinity, a sub n, x to the n equals 0. Okay, so we want to, get to the point where we combine these and find a recurrence relation, find some coefficients, and get our goal of, two power series solutions. So let's go ahead and get to that point. So one thing we would need to do is distribute in this x inside the power series. And so we have an x to the n there. So those two powers would just add to each other. So your basic algebra powers adding. So let me just rewrite the first term, and what I would have now is a sub n x, and now it's to the n plus 1. Okay, because think about x having like a power of 1. Okay, great. So we've done a couple of these previously, but yeah, we want to combine into this into one power series. So there's a couple of things we need to do. We need an index shift. Maybe we need to peel off. So the first thing I'm going to do is make sure we all have x to the n. So here I'll say is now we want to have all x to the n. So what I want to do first is index shift. So we're going to index shift both terms. And so I'm going to index shift the first term. And so I want to get x to the n. So I need to add 2 to all the n terms in the series and subtract 2 from the index. So I would have n equals 0, n plus 2 times n minus 1 plus 2 would be n plus 1, a sub n plus 2, and then x to the n. Okay, plus the next series. So I'm going to index shift this. I want x to the n, so I'm going to subtract 1 from every term in the n in the series and add 1 to the index. So this would be n equals 1 to infinity, a sub n minus 1, x to the n. And it all equals 0. Okay, great. So we have everything in as x to the n. Great. What we want to do now is get the same index. So, we could say now we want the same index. And the only way to do that is if we get up to n equals 1. Okay. For both. So what we're going to do is, peel off n equals 0 from the first term. Okay, we're going to peel off n equals 0 from the first term. So if I peel off n equals 0 from the first term, what this would look like is, that means I'm plugging in n equals 0. So this would be 2 times 1, a sub 2, and then x to the 0. And we're still adding it to the series. We're now starting at 1 because we peeled off that n equals 0 term. So n plus 2 times n plus 1, a sub n plus 2, x to the n. So I'll put brackets around this just to show like that's that first term. And then our second term stays the same. And all still equals 0. Okay, and this is, I could say like this is when n equals 0. Okay, great. So we have the same index. We have the same x to the n. And so what we can do now is combine. Okay, so what this would look like is 2a sub 2. I'm going to leave this as x naught plus the power series n equals 1 to infinity. And then I'm going to put some brackets here, like just to show that, we factor out the x to the n. A sub n plus 2 plus a sub n minus 1 x to the n, all equals 0. Okay, great. So we want to get what our constants are. So remember our goal, like we want to get to this point right here. Two power series and two constants essentially. So, let's go ahead and see how we'll get that. And the way we would get that is with the recurrence relation. So we're going to use the identity property. Oops. Okay, and that the only way for all this to equal 0 is if the coefficients equal 0. So that means that, you know, 2a sub 2 equals 0. And the constants within the power series, n plus 2 times n plus 1, a times a sub n plus 2 plus a sub n minus 1 equals 0. So we need to now set up this recurrence relation. Okay, we need to set that up to determine what those constants are. To determine the a sub n's. Maybe I could clean that up a bit. That's a little better. Okay, and when we do this, just keep the idea in mind that, we always, oops, we always solve for the higher a sub n's. Okay, so in this case, you know, I'm looking around here, I have a sub 2, I have a sub n plus 2, I have a sub n minus 1. I'm going to solve for a sub n plus 2 for the recurrence relation. Okay, so let's go ahead and get started on that. So I already have kind of one that doesn't really need a recurrence relation. I could just solve for a sub 2. So that just means a sub 2 equals 0. Just divide 2 over. And so a sub 2 equals 0 for n equals 0. Because that's what, the term was when we peeled off. Okay, so now what we want to do is set up the recurrence relation. So, we have that n plus 1, n plus 2 times an plus 2 plus an minus 1 equals 0. This is the highest a sub n, so we want to solve for it. And so our recurrence relation is going to kind of fast forward the algebra here, but I would have an plus 2 equals negative an minus 1 all over n plus 1 times n plus 2. And this was for n equals 1, 2, 3, etc. Because a sub 2 is for when n equals 0. Okay, so we have this recurrence relation now, right? So what we're going to do is use this recurrence relation to get two solutions in terms of A naught and A1. So that's going to be our goal, right? Get two solutions in terms of A naught and A1. So we need to use this recurrence relation to get that out. So let's just start by one. So for n equals 0, right? We already know what that is. A2 equals 0. Okay. We already have that. I just wanted to keep it here, just to keep it within the data. And so for n equals 1, I'm plugging in 1 into this, all the n values here. So what that is that would be A3 equals negative A naught over, 2 times 3. And that's negative A naught over 6. And so A3 equals negative A naught over 6. Okay, so that's 1. Now for n equals 2, if I plug in 2 into my recurrence relation, I would get A4. So this would be A4 equals negative A1 over 3 times 4 equals negative A1 over 12. So that means I have A4 equals negative A1 over 12. Okay, so let's do a couple more. I need some more A1s and A0s. So plug in n equals 3. I would get A equals 5. That would, if I plug 3 into my recurrence relation, I'll get negative A2 over 4 times 5. Okay, but remember that A2 is 0. So I could plug in 0. This would be like 0 over 20, which just equals 0. So that means A5 is just 0. Okay, so a bit strange. We're getting a 0 value now, but let's keep going. N equals 4. If I plug in n equals 4, I get A6, negative A3 over 5 times 6. That's negative A3 over 30. But I know what A3 is, so I can plug A3 back into here and get it into terms of A naught. Okay, so this would be, let's see, negative A naught over 6 all over 30. And that turns into positive A naught over 6 times 30 is 180. So that means A sub 6 equals A naught over 180. Okay, so let's see. We have about, in terms of A naught, we have 1, 2 constants. And for A1, we only have 1. So I want to get one more. So this would be n equals 5. I would get a sub 7. I would get negative a4 over 6 times 7 equals negative a4 over 42. And I know what a4 is. Okay. So yeah, we're going to get another term for a1. So I'm going to plug that in. This would be negative a1 over 12 over 42. And this would be negative, oh, excuse me, it would be negative negative, so it would be positive. Be careful with that. Easy to make mistakes here. So this would be a1 over 504, which gives us a sub 7 equals a1 over 504. So now I have a second term in terms of a1. Okay, so what were we doing all of this for, right? Um, Once again, I keep reiterating this, but we're trying to get a series that looks like this, right? A0 times y1 plus a1 times y2, where y1 and y2 are power series solutions. So, you know, we want, you know, the power series solution for the differential equation to be this. Y equals the power series n equals 0 to infinity, a sub n x to the n equals a naught plus a1 x plus a2 x squared plus a3 x cubed, etc., right? So what we can do, we have all of these like a1, a2, a3, a4, a5, a6, a7. We can substitute all of our ANs. Okay, we could start substituting all of those in, and we can get an idea of what our power series could look like. And we eventually get the two of them. So we would have y equals a naught plus a1 x, because, you know, we were really given those a naught and a1. We kind of start out at a equals 2. So a naught and a1 are just themselves, but then we go ahead and start plugging in our values. So a2 we just saw was 0, so it's be like 0x squared. A3 is negative a naught over 6, so plus negative a naught over 6x cubed. Okay, and we'll just keep plugging them in. So a4, if you look above, is negative a1 over 12. A5 A5 was 0. Okay. A6 was a naught over 180. And A7, that's the last one we got, was a1 over 504. And yeah, we could keep going forever, but we do not want to. We just want like maybe one or two A1s and A naughts. So let's clean this up a bit. 0 goes away. Here and for x to the fifth. Okay, so I get a solution like a naught plus a1x minus a naught over 6 x cubed minus a1 over 12 x to the fourth plus a naught over 180 x to the sixth plus a1 over 504 x to the seventh. Etc., etc. So said this a bunch of times in this video, but yeah, we're trying to get to something like this, right? A naught times y1 plus a1 times y2. So what we can do in our solution now is group together those a naught and then group together those a1 terms. So let's say group A naught and A1 terms. So if I do that, what I end up with is A naught times 1 minus 1 6 x cubed plus 1 over 80 x to the 6 plus dot dot dot, because it goes on forever, plus A1 times x minus 112 x to the 4th plus 1 over 504 x to the 7th plus dot dot dot. And these parentheses, these functions of x, all these terms, well, that's what that y1 and y2 are. So therefore, I get the y equals a naught times y1 plus a1 times y2. Okay, so that is my answer. Okay, so yeah, a lot of work. These power series solutions take quite a while to do, and you just got to be careful with your algebra, right? Um, Algebra with index shifting. Okay, algebra with your index shifting, algebra with your peeling off, algebra with finding your recurrence relation, and algebra with getting your terms. Okay, so be careful with those. That's the backbone of this work. Okay, yeah, we're doing some differential equation work, some calculus work, setting this up, but a lot of it is algebra working with series. Okay, but yeah, you want to get to a solution where you have, a naught times plus y1 terms of x plus a1 times y2 solution. So yeah, that's it for this video. Thank you for watching, and I'll see you in the next one. Take care.